All right. Welcome, everyone. I'm waiting for the last people to get seated, and then we can start. Okay, you guys in the center also be quiet. Amazing. Okay, I believe I have everyone's attention. Welcome to the introduction workshop of the AI Cup. My name is Rijn. I'm the chief engineer at Epoch, and together with Willem, one of our ML engineers, we'll be giving you an insight to how to compete on Kaggle. All right. We're going to go through a couple points today. We're going to start off by exploring the Kaggle page. How does it work? How do you make submissions? How to use the GPUs, etc. The bulk of the workshop will contain us going from all the way from zero. We'll do some data analysis, train a model, and make a submission. Afterwards, we'll go over some finishing touches, the rest of the Kaggle platform, and finally, we'll leave you off with some ideas for some future improvements. I'll start off by showing some of the data analysis and the Kaggle platform, and then Willem, who is sitting in the front, will take it over and actually do some of the modeling and making a submission. All right, if you guys haven't already joined the Kaggle page already, here's a QR code. I would like to mention, however, that if you want to follow along on your laptop, it might be inconvenient to scan the link, so you can also find the link on our website, which is teamepoch.ai. And then should be able to navigate to the page of the AI Cup. All right. Waiting for the last people to scan. Okay. Wait, one slide ahead. All right, I'm going to go to the Kaggle page as well. So this is what you see when you land on the Kaggle page. First off, I'd like to go over a couple pages. We start off with the overview. This gives an overview of the competition. This is something you can read through during your own time. A couple important things to note as the timeline. I know we went a lot over this before in the previous presentations. Please read this through during your own time. There are some other sections which I'll go over later. The evaluation metric, we also went over it before. But the interesting part is probably the data section. So here, you go over to data, and you can see the data. And the first thing, what I usually do is I have a look here and kind of see what type of data are we working with. And as you can see here, it's a CSV, so a comma-separated value. Sometimes they're images, sometimes they're videos, point clouds, etc. Here they're just CSVs. Yeah, real quick.
The website is the link for the Kaggle.
It should be under AI Cup. There should be a link somewhere.
Yeah, I can find
You can't find it?
it. On your email, if you search in the email. How you found it? Thank you very much.
Okay. I'll continue. So right here we have two CSVs. And there is a train CSV. So this is the data you use to actually train your models on and do your own validation. And then finally, there's also a test CSV. And this is where you do tests on, where we evaluate how good your model actually is. This is what you'll be scored on. And finally, there's also a sample submission file, which shows the format of how your submission is supposed to look like. In the train CSV, there are two parts. The first part goes over the radar data. We have several columns, namely the track ID, which is a unique identifier of a track. So every track needs to have a classification per bird group. Then there's some information on when the radar started tracking the object and when it finished. We have the trajectory, and this is the most important column, because this encodes how the bird flight. We'll go over that later, how to decode that and actually make something useful out of it, actually interpret it. We have some information on the trajectory time, so the time since the start of when the radar started tracking. So you see every single position in the list of measurements, you get to see the timestamp, and from this you can get stuff like the sample rate, for instance. We also have some information on the radar bird size, the airspeed, and some altitude stuff. So this is present during training time and also during testing time. So you'll be using these columns, and you can maybe generate your own features to do predictions. And then in the train CSV, we also have another group of columns, which are things that the observers made. Most importantly, it's the target. It's the bird group. So is it a pigeon? Is it a cormorant? That's what you're supposed to classify. There's also some additional information, like some IDs, the position, how many birds the observer said he had observed. This doesn't mean that there were actually 20 birds, but the observer said there were 20 birds. And sometimes there's a comment, not always. And this is the format of how you make a submission, which you can also see in the sample submission.csv. I see that I should probably join the competition. You should read through the rules. Accept. Yep. And now I can actually see the data, if I'm not mistaken. Perfect. Okay. Now I'd like to go back to the slides and explain a little bit more how the data set is split up. So the entire data set is about 4,000 rows, of which one part is used for training and one for testing. So ideally, we would like to give you all the data, all the 4,000 rows, so you can have more data to make better models. But we also need to have some data to evaluate your performance, to see how good you guys actually did. And for this reason, we have the test set. This test set is also split up into two sets, the public test set and the private test set. And this sometimes raises some questions. Why would you do this? Well, the reason is every day you get to do 5 submissions. And especially since the data set is quite small, if you make 5 submissions every day, you can start to overfit to the test set. And we don't want you guys to overfit to the public test set. And that's why there's also a private test set. So what happens during the competition, you make a submission, and then you see your score on the public leaderboard. All the way at the end of the competition, your private score will also be shown. And the private score, that's the score which counts in the end. So this is really important to know, especially because the public set is a lot smaller than the private set. It can also be a bit more noisy. So sometimes you see your score go up, and you're like, oh, amazing, the model is a lot better. But because the public set is quite small, it could be a bit of noise. So that's good to know. This is something that happens a lot in Kaggle competitions, especially when dealing with a small data set like we are here. And in a previous competition we joined, we also experienced this. In machine learning competitions, we call this phenomenon shake-up. So as you can see here, previously we were 150th out of the 4,000 teams. And then once the public set was revealed, we dropped a bunch of places. Luckily, we still were able to get a bronze medal. Okay, I think I can go back to Kaggle. All right, so I went over the data. Now here, this next part is the code. And this is where you can actually make some code. So I'll start writing some code. You can make a new notebook here. And right now we are in a Jupyter notebook. This is an isolated containerized environment, which is quite useful, which can do a lot of stuff. And I imagine most of you have worked with Jupyter notebooks before, so I won't explain exactly how that works, but you can do stuff like you can make a print statement like hello from AI Cup. And I have to wait for the kernel to start, but it should be quite fast. Another thing to know is kind of the hardware you are working with. If I'm not mistaken, you get 4 cores of CPU, 2 CPU cores. You can also use a GPU, which is useful if you're training any deep learning models or doing a lot of image analysis. If you want to do that, you could go over to settings, if I'm not mistaken, hit accelerator, and choose the GPU you would like to use. I think you have 30 hours of quota every week, which Kaggle provides free GPU usage. Okay, so now you see that this Python code executed. Another thing you can do is you can type shell scripts, which sometimes is useful. So you can do echo hello, and that also works. Okay, we are working with a containerized isolated environment, and there are a lot of packages already installed. So if you're working locally, you might use pip, for instance, to install some packages like NumPy. You like pip install NumPy. Here, a lot of packages are already installed. So if I do import NumPy as MP and do like this, Oh, I missed one. This already works. You don't have to install packages. If you want to know every package that's installed, you can always run the pip freeze command. Since there are a lot, this should take a while. So okay, so now you might be thinking, cool, but I want to use a very niche package. That's also possible. So for this, you can install it. A package which could be an example is Skyfield. So let's say I want to use Skyfield. And then if I import it, it says no module name Skyfield. What you can do then is you can go over to the settings, or add-ons actually, and go to install dependencies. And then here you type pip install Skyfield like that. Important to run. And now in the console, we see that this should execute. Should go quite fast. And now it says, note, you might need to restart. From experience, I don't think so. Let's see. No, not the case. So now this works. All right. I think I explained a bit of the Kaggle environment and the GPUs you can use, etc. Now let's actually load the data and start exploring the data a bit. Let me make a nice markdown block, and let's say, let's load the data. Cool. Over here, since we made this notebook through the competition page, automatically you can already see the competitions, you can already see the competition data. I would also like to mention if you want to make models on your local machine, you can always download this. But right now we're working in the Kaggle environment. Is it the case that you want to use some other inputs? You can always add inputs here, and you can find datasets which you can upload yourself or find on Kaggle. You can upload models, etc. But right now, we will only be working with the competition dataset, which we already have loaded in. So for loading the data, let's use pandas. Let's import pandas as PD. And let me close the console. And let's make a train data frame. And here, if you hover over this, you can just copy the path, which is quite useful. Also, one thing I forgot to mention is over here you can see your system resources. So you can see how much CPU you're using, how long the session has been open, how much RAM you're using. This is incorrect. This has to do with my laptop settings being a bit weird, but that's besides the point. All right, so we should have loaded the train data frame. Now let's also load the test set. Let's do the same. Let's read the CSV. Okay, now let's quickly inspect, see how it looks like. So when I execute the cell, you can see this is the data set which you also just reviewed. So we have the same columns, we have the track ID, some radar information, time, etc., etc. Now one thing that I notice is that you have the track ID as unique identifier. And what I usually like to do is I usually like to set since it's unique, I usually like to set this as an index, so later we can easily compare our predictions with the ground truth. So let's do that real quick. Pandas, you can do set index. And we want to set the index on the track ID. That's also, whoops. Let me also do that for the test set as well. Might be the case that this is not in place. Let me check real quick. It's not, so I have to assign it. The same one for the test data frame. All right, okay. So now that we've loaded the data, I think it's time to kind of explore and make some plots. I know you guys already saw some plots Joop showed at one of the presentations, but I'd like to make a couple of our own. Add some nice markdown. Let's explore the data. Cool. Okay, so when we're looking at this data, there are quite some columns. And one really important part is to do some data analysis and to ask some questions. So there's a lot of questions you can ask. And the more plots you do, the more questions might occur to you. Like, oh, this is interesting. Let me look into this a bit more. One thing I always like to start off with is kind of having a look at the target distribution. So our targets here is the bird group column. So let's have a look at the targets. So let's get the train data frame, and let's get the bird group column, and call value counts with Python, with pandas. Once we execute this, we can see that there are a lot of seagulls and a bit less songbirds and a bit less pigeons. I think it's nice to show this in a plot. So for this, let's import matplot lib.pyplot as plot. Just plot this real quick. Oops, accidentally hit enter. For this, let's also get the format. Let's do, let's say, 1 decimal, and add a percentage, and do plot.show. And again, as you can see, it's going correct. I messed up somewhere. Because I have to indicate that I'm doing formatting. Perfect. So as you can see, almost 60% of the training data are seagulls, which is a lot. So it's important to really understand and realize that there's a huge class imbalance, and this might influence your modeling decisions. Okay, we've looked at the class imbalance. Now let's have a look at this trajectory column. Oops. I accidentally, probably needs to restart the session. Apologies. Just hit run all real quick. Perfect, still memory. Okay. Okay, so let's inspect one of these trajectories. So let's go over to here, type in trajectory. Let's get the first one and print it. So as you can see, it's a very long string of hexadecimal. And this, I have no idea what's going on, so let's try to decode this. And for this, there's a library we can use, which is, this does not work, is from Shapely import well-known binary. So with this, we can actually decode what's going on here. So let's type the geometry. I have to look real quick at my notes. Forgot the command. Let's have a look. I did this. Right, okay. So let's get let's load it. If we want bytes, it's from hex. And let's actually assign this to a variable. Let's call it binary hex. Oops. This. Put it here. Let's get the coordinates. Let's do. First, let's actually see how this looks like. The nice thing about working in Jupyter Notebook is that I can actually visualize some of this. So this is a geometry object. You can already see the trajectory. But we want coordinates and not just the geometry. So what we can do is go like this and assign, call the chords attribute. So now if we print chords, we should get a list of tuples. And every tuple is a point in time. And so the 0th row is the longitude, then the latitude, then the altitude, and finally the m value. And here the m value is radar cross-section. So this is all cool and such, but let's actually apply this to our data frame so we can expect it a bit more. So for this, let's make a function. Let's define a function and call it split the x, the y, the z, and the m value. And as an input, let's give it the well-known binary hex. And now we want to do a couple of things. So first, we want to do the same transformations we just did. So we want to get the well-known binary hex, we want to convert it to a Shapely geometry object, and then extract the coordinates. So let's do that real quick. So now that we've done this, we want to go over the next step. So as you can see, there are a couple of columns, but what we actually want to do is we actually want to zip these. In Python, there's a nice zip command to do this for us. Let me check real quick. Let's have a look. Right, okay. So you want the x's, the y's, the z's, and I'll call it the RCS's. And let's zip that. So it's a list, as you can see before, so we need to unpack the list of chords. Okay, and finally we want to return a pandas series. So we want to return all the columns. So right now we're getting the well-known binary hex from the trajectory column, and we want to return 4 new columns. So we want to return the columns of x's. Let's assign that as x's. Same for y's. And with x and y, I mean longitude, latitude. Y's, z's. And let's not call it like that, let's call it like this. The y column, the z column, and finally the RCS column. Hope I did not make any typos. Okay, now that we've made this function, do some functional programming and actually apply it to our data frame. Let's make some extra train columns and get the train data frame and apply this function we just created on to the trajectory column. Trajectory. This is the name of the function which we apply. Let's see if this worked, if I didn't make any typos. And as you can see, these are our extra columns. But what we want to do is we want to actually join this to the columns we started off with. Let's get the train data frame again. And join this with the extra train calls. And again, this maybe we have to assign it. I always forget. No. So we need to go like this. Oh, I was printing the wrong one. Perfect. So now we see the same train data frame, now also with our new columns. And finally, we should also do this for the test. So it's extra test calls. This is our test data frame. Let me just copy this. Let's see. Whoops. Test df. Cool. Spot the test data frame just to be sure. Print. And found their extra test calls. Whoops. Still an error. Oh, let's see what went wrong. We run all. Perfect. Okay. There we go. Bear with me. Now that we've actually extracted these trajectories, let's make one final feature, which is interesting to plot. So we have this radar cross section, which is a list in decibels per square meter. But it might be interesting, let's just say, let's get the average. So for this, let's do in the same format. Let's do the train data frame is the train data frame where we apply the mean. Oh, I should make a new column. Let's call the column the mean radar cross section and apply the mean. I messed up again. Probably have to run all. Yikes. Okay, I see what's going on. I'm applying this to the entire data frame, and I only need to apply it, of course, to the radar cross-section column. This is the first time I've ever done any live coding, so for me it's also a fun experience. All right, so let's do the same thing for the test data frame. Let's make the new column, the mean radar cross-section. Let me just copy this over. Like that. Check if I did it correctly. As you've noticed, it's useful to check if you've done stuff right because I'm making some mistakes. And as you can see right now, we also have a column called the mean radar cross-section. Okay, so we went over we loaded the data, we had a look at the target distribution. Now let's also make some plots of the numerical stuff. So let me make a list real quick of numerical plots I want to plot. So I'm curious to plot the following things. Let's see, I want to plot the airspeed. Let's do the maximum altitude, so airspeed. Let's have a look at the maximum altitude. And let's have a look at our new feature we just made, the mean radar cross-section. Okay, let's loop over the features that you want to plot. So for each feature in our list, calls to plot. Oh, for feet in the list, we want to make a figure real quick. Let's do a figure. Assign the fig size to a tuple. Let's do 12.6. I like to use Seaborn personally for some nice colors. So let's import Seaborn real quick. Right, and now let's make a box plot. So let's do, so the data is equal to the train data frame. So right now I want to make a box plot of the following features, and I want to compare this to the bird group. So kind of see how does the airspeed differ for each bird. So maybe some birds fly faster than others, maybe some slower, and I want to check this out for every string in this list. So let's do that. So the data is this. So on our x-axis, I like to have each bird group. So that's the bird group column. And then on the y, I want to have the feature. Finally, since we're using Seaborn, I always like to add a color palette to make it nice and pretty. This is not necessary, but I like to be fancy. We also need to assign a hue. So this palette, the Verdis, is basically a range of color, and we want to distribute this across the x-axis, which in this case is the bird group. And now to wrap up, let's quickly add a title, pot.title, and let's call it comparing the feature, let's say feature per group. I think that makes sense. Let's quickly set pot.xticks, the rotation to 45 degrees. I'll show the plot. Okay, hope I didn't make any typos. Let's execute the cell. And I made a mistake. I probably, rotation xticks.
No underscore.
No underscore? No underscore. Thank you, Willem. Okay, we have a couple plots I'd like to go over. First, the airspeed. We can see that the color column has a lot of variance. So the whiskers are really big. There's a lot of difference in this group. So just airspeed alone is not really useful to distinguish clutter, but maybe in combination with other features, it might be. Some notable examples, the birds of prey fly a bit slower. They're probably soaring and catching the thermals. And some other birds are a bit faster, like pigeons, for instance. Then we have the altitude. You get a little bit of an idea. For instance, let's have a look. The waders fly a bit higher, but again, there's also a lot of variance in this group, so it's hard to really say anything based on this alone. And then finally, the mean radar cross-section. And here we see a little bit more information. Again, quite some variance, but we clearly see that the geese are bigger. Makes sense, they're also bigger birds, so they reflect more of the radar. Okay, thank you. So right now we've explored some data. Now I'd like to invite Willem to go over some of the modeling.
Nee, gewoon terug naar Kaggle.
Okay.
All right. Let me see. Get this mic working. It is indeed working right now. So once we've done all this analysis, you can of course do a lot more. We're going to stop at this for this workshop. We're going to actually start training the model. And for that, we need to make our data in the correct format that the models are going to use. So we're going to do prepare features. And for that, you gotta get back to your machine learning basics and know that a model needs two things. It needs an input. It's a model input, which is denoted with a capital letter X. And it needs model targets, which is denoted with a lowercase y. In our case, we're going to just select 5 features, which in this case are going to be the airspeed, the maximum Z, also the minimum Z, the mean RCS, and another column named radar bird size. So we're going to quickly grab those. You can, of course, select a lot more, but for this workshop, we're going to only start with these 5 basic ones. Let's see, mean RCS. And we're going to get the radar bird size. So now to actually prepare our data, we're going to get our training data. So from train df, we're going to select these columns. So we're just going to do features. We're going to do the same for the test set as well. So x test is test df features. And then, of course, we need our targets, which is only available in the train df, which in our case is going to be the bird group. So make sure this actually works, we're going to print it. So for this case x, we see we only have here our features that we're going to feed into our model. And then we're also going to quickly check our y. And you can see here there's the same track ID here as the one at the top here. And in this case, these model inputs then classify to a waiter, and then the next model input classifies to a goal, and so forth and so on. So now we're going to set up the pipeline. A pipeline is a way for which your input data actually gets fed into the model, and then a prediction will be made, which you can then compare to the actual target. So we're going to set up the pipeline. For that, we're going to use packages from sklearn. Maybe in your machine learning courses, you've been really taught to always make your own implementation, while for competitions like this, it's really not necessary to create stuff that's already been created 1,000 times before. So for this, we're going to be using from sklearn.pipeline import pipeline. Pipeline is really easy to use. You can just give it your input data, and it will do all the training validation, all that stuff for you. We're going to set that up. So you can give a list of things you want your pipeline to do. In our case, we're going to do some pre-processing, which I will get to in a second, so I'll just leave that empty for now. And then we need our actual model, which we're going to train. In this case, we're just going to use, again, a basic model from sklearn, in this case, a histogrammic gradient boosting classifier. How this model exactly works, you don't need to fully understand to just make a submission, because if you want to go to dive into all the details yourself, all the details you want to do that yourself. Essentially, it's just a decision tree, but then uses some fancy tricks to make it better, hence the histogrammic and the gradient boosting part. To make it consistent, we're going to give it a random state. So if you run this model multiple times, it will give the same output, which we then also have to import. Then we're going back to our pre-processing. So we go back to the data we've selected, the gradient decision boosting, decision tree we're going to use only wants numeric features as its input. And in this case, this goes well for airspeed, for minimum Z, max Z, mean RCS, but it doesn't work for radar bird size, since that's a string, and it doesn't know how to deal with that. So for that, we need to do some pre-processing. In this case, convert this string representation into some actual numeric values. For this, we are going to use a concept called one-hot encoding, where essentially you replace this single column with multiple columns. In this case, how many unique values are in this column. In this case, there are 4. There's a small bird, a medium bird, a large bird, and a flock. And it will then be like a binary representation which one it is. So for example, you have a small bird column, a medium bird column, a large, and a flock. And then for the first one, it will be a 1 for small, and then here will be a 1 for large, and 1 for medium, and for the rest it will be 0. So we're going to set up the preprocessor. We're going to use, again, stuff from sklearn, which then needs a list. So in this case, the one hot encoder. I won't explain in detail how this works. If you have some more questions, you can ask them at the end. But then we also need to specify which column we want. In this case, we want the radar bird size. Again, you can also write your own functions for this, but again, we're going to use what's already there. And then we also specify what we're going to do for the remainder, which in this case, we're just going to pass it through. And then now we have our preprocessor set up, we can put that into our actual pipeline. Preprocessor. So now when you call the pipeline, it will first feed the data through your preprocessor and then feed your data into the model, and then you can make a prediction. So once that is done, we're going to actually set up the training. But before that, we actually want to decide what we're going to actually train our model on. So we're going back to the slides. So remember this slide from the beginning. This is how the data is split. You get 2,600 samples to train on, and then we're going to check your performance on the other roughly 1,900 samples. So for this means you have for 2,600 you have the tracks and you have the answers. You can just train your model one time on all the data, and then make a submission and then hand it into the leaderboard. Which in theory just works. The only problem is you only have 5 models, 5 submissions a day. I mean, you can essentially only submit 5 things a day, which isn't a lot if you want to test like multiple things, try some different strategies. Oh. I hope it comes back. For that, we can split off a section from our train set to be like a sort of proxy on how well your model will actually perform. And in this case, it's quite typical to split off 20% of your data. In this case, we call it the validation data, which you have the answers for. So in this case, you can train your model on this 80%, then make a predictions for the other 20%, which the model has never seen before. And then you can compare what score you will get from that 20%, which then should be, if that's higher, then you should also get a higher prediction on your leaderboard. Meaning you can save all the submissions by just only computing on the 20%. But this is still not perfect, since you now are wasting 20% of your data, and you're only training on 80%, while you have been given like 100% of the data, which is why it's very typical to employ what's called a cross-validation strategy, where you essentially not do it only once, but you do it 5 times. So you split your data into blocks of 20%. Usually you do this randomly or semi-randomly. And then you train your model 5 times, train it on the 80%, and then validate it on the 20%. And then you do this, you make sure the block of validation keeps splitting until at the end you have made a prediction for 100% of your training data. And then you can use the labels we have provided you along with the scoring function, which I will get to in a minute, to create something called the out-of-fold score. All these predictions are the out-of-fold. They are not in the training fold, hence they are out-of-fold. And this should be the best idea of how well your model is actually performing. So if you can try to optimize this locally and then make a submission, and then in theory, if this is higher, then your leaderboard score will also be higher. Mids, you don't have any weird data leakage problems going on, so that your training set actually knows stuff about the validation, which could be a problem here, or could not be, depending on how you set up your pipeline. So now it's time to actually make our model. So for this, we're going to set up the cross-validation. Again, we're going to use stuff from sklearn. So from sklearn models. We're going to use stratified k-fold. I will explain in a second what stratified means. What stratified means, you can do the split fully randomly, but in our case, we have quite some big division in our data. And what stratified means is that at least all splits will have a equal representation of each of the classes. So instead of doing it fully randomly, it at least has some bias that not, for example, one validation fold contains all the cormorants, while all the other things don't. You at least want to have a equal representation. So we're going to then define how many splits we want, which in this case we're going to follow the examples from the slides, which is 5. And we're going to set up our cross-validation. Okay, fold. Then we have to define how many splits we want again, which is going to be n_splits. Then we are going to shuffle the data, just in case any weird grouping has happened during the creation of the data. And again, we're going to make it consistent by giving it a seed it can use. So every time you run it, it should provide the exact same split. Then to actually split the data, you can do cv.split, and then you can give it our input data, which is our x, and our targets, which is going to be our y, and it will automatically stratify over these targets you specify here. We have to convert this into a list again. And now we can see if this actually worked. So for I in split, I'm going to print out how big the things are. To train, I seem to have fucked up. There we go. The length of training index. And then for val, we're going to do the same thing. But then do the val index. So now we're going to run this. I seem to not be able to type.
It's a random state instead of null state.
You are
Also, you
complete.
have the previous import pipeline.
What?
In the previous code block, you import deep line.
No? Oh, here, yeah. I make that mistake quite often. I don't know how it didn't break then. I didn't run this. All right, let me confirm. Trends for trends.
Should be in strings for the label. Preprocess and model should be string in the pipeline.
Where? In the pipeline? Oh, yeah.
Yeah.
All right, seems to have worked now.
Space.
Yes, I figured out. Random state. And I forgot to enumerate. So now we can see here. Thank you for the pity applause. Fold 1 will have, for each fold, will have roughly the equal amount of training and validation samples. Of course, the training isn't exactly divisible by 5. So in this case, only one fold has an additional sample. So now that we've done this, we're actually going to train the model. Train in. Oh my god. Right then. For this, we're just going to copy paste whatever we're doing here, since we're going to do the same split. And then we're going to use the split to actually select the right data. So we're going to do x underscore train. It's going to be our x at our training index. And then y underscore train is going to be our y at our train index. And then we're going to do the same for our validation part. So now that we've selected their data, we're going to actually start training our pipeline. So we're going to do pipeline. Just going to clone the pipeline. Again, it's a function from sklearn. And to train the pipeline, you simply do pipeline underscore fold. Let me scroll down a little. Dot fit, and then you give it their input data, which in this case is x train, and then your targets, which is going to be y train. So this will train all the model for you. And once that is done, we're going to do our predictions on our validation set. So we're going to do val predictions. It's going to be pipe. I seem to. Oh my god. Pipeline fold dot predict. We want the probabilities in this case. That's how the metric wants it. Predict proba. And then we want our validation data. So this will give us our predictions. As, in this case, we're just going to combine all the predictions together. So we're going to create an out of fold predictions, which is going to be a data frame. We're trying to fill with zeros in this case. I'm going to set the index to be x.index. And our columns, which we have to grab from our targets. So classes is np.unique from y. So here we can save all the predictions for the entire train set. So to overwrite it, we simply do of preds.illoc at the val index is going to be the val predictions. Well, we have trained this pipeline. We're also going to make predictions on our test data, which we can do in pretty much the exact same way. And it's going to be x underscore test. And then again, we want to also save these predictions somewhere. In this case, we're going to use an np array. np.zeros, for which we want the sizes to be the length of x test, and then the length of classes. So now we can do test spreads is plus the predictions we made. Since we make a predictions on the entire data set, we want to combine them during all the training and then average them at the end to get like a single prediction for each of these samples. And then we're going to do some printing at the end to make sure we know stuff's actually happening. Trained fold. So now when we run it, clone. It is without the capital letter. It is indeed. Zeros. So now, is it indeed training our fold? It is trained the first fold, then it trains the second. This will go on until the end. So during each fold, a model is trained, and then the model is used to make predictions on the test set, and that's then averaged. And at the end, it is done. We can quickly look at how these things actually look. So we can do our out-of-fault predictions. Okay. So going here, we can see here we have this track ID, and then you can see all the probability of how certain it is a certain class. For example, for this track ID, it's really certain that it's a goal. Here's also certain that it's a goal. While here, it's, for example, quite certain that it's a songbird. This is exactly what the metric wants. And now, since we have all these predictions, we can calculate what our score would be. For that, we can go back to the original Kaggle page, which we do not have open. So just do it like this. So we can see it here. This here has the evaluation metric. We're using a metric called average precision. How does it exactly work? We don't really have time to explain it. You should do the research on your own time. But what we do provide is a notebook of the implementation of the metric, which we're going to open. So here, this is essentially just a copy of how the score works on the Kaggle platform. So in this case, you can just fully copy this code. And then we're going to go back to our notebook. And then refresh our notebook. So then we're going to just paste the scoring function into here. What this needs a solution, so essentially the correct answers, and it needs a submission. And in this case, our submission will be our out-of-fault predictions, and our solution we have to quickly make. For that, I will not be writing the code, but I will just be pasting it from our reference solution, which in this case is going to be this. So now we can just very easily calculate our score by doing OF score. And then we're going to do the score function, and we're going to give our solution and our out-of-field predictions. And we're going to run this one, and then we're going to print our score. All right, let's do an F string. So in this case, we can see our local score is 0.38. The metric runs from 0 to 1. I mean, and 0 would be your lowest score, and 1 would be the highest score. So in this case, our score isn't very high. But again, that kind of makes sense as our model is very simple, and we're going to use 5 features to actually train. What is also, since we also have these predictions, we can also do some additional error visualization, which I will just be copying from here. We have to import. And then I need to change this. So in this case, a confusion matrix is made. How a confusion matrix works is that you have your, for each of samples, you have your predicted label, so what your model thinks the sample is, versus what the actual true label is. So in this case, you can see that it is predicting for almost all classes very often a goal, which makes sense because goal is by far the most common class, and the features maybe aren't enough to fully be able to classify which species it is. But it's noticeable that you can see here clutter is actually being classified correctly quite often. 60% of the clutter predictions are actually correct. And also here for songbirds, which is the second most common class, it's also doing relatively well. But for example, for here, for cormorants, it's getting absolutely 0 predictions correct. So our model isn't good, but it's good enough for now. And then the final step we have to do is actually create our submission, which is going to be another data frame. For this, we're going to get our test predictions. Since we have the data of 5 different folds, we need to divide it by 5. Since we've added it together, we need to then average it at the end. Or I can do it end splits, just in case that ever changes. Then we got to get the same index. And we're going to get the same columns. And then the only step we need to do after this is actually convert this to a CSV. And it's very important that you call this thing submission.csv. Because when you hand in a submission, it will look for a CSV with exactly this name. And if it can't find it, it will throw an error, and you might lose one of your 5 submissions in the day. So after that is done, we can just do a final print statement. Saved to submission. And then we can circle back to the bash command. We can see that it actually exists. In this case, that seemed to have worked. So save to submission CSV, and then you have the track ID. So this is from the test set, and then you can see that prints the predictions for each of the classes. And again, this column seems to be by far the highest, more than 99%, which I believe coincides with the goal class. Or the pigeons, actually. It could be the pigeons. But now that we have done all this coding, we can actually make a submission. You can do that in multiple ways. In our case, you can just press the Submit to Competition button here. Then you can submit. You can just submit an entire notebook. And then it says here, your submission file must be named submission CSV. That's why it's very important to name it that. And then you can give it a name, so let's call it intro workshop. And then press the submit button. And you can now see in the bottom right, it's currently working. It's building the dependencies. We've done at the beginning, so it's currently making the package we're installing. And in a second, we can also see its actual progress. So we have to wait a second. So you can see now here it's running. You can open it. And you can actually see all the logs that's happening. Just ignore this time for now. That is bugged. For example, it's successfully installed Skyfield. And then you can see the actual output. So it will circle back to all the printing, all the data analysis we did. So hello from AI Cup. And NP is not defined. Seems like someone commented out the line. Can do a quick run all again. Here it sees training again. Wait for it to finish. And there it's done again, so we're gonna try it again. And here it's also then complete submission not found. And let me see if that actually cost us a submission for the day. It did not. So this is the second way to make a prediction. You can, if you train it locally, you can press the submit prediction here and then upload the CSV yourself. Or if you have a notebook already running, you can select the CSV from here. In this case, it's running again. And once that is done, you will able to see here at submissions. this case, no submissions filed, so we gotta wait a few more seconds for this to be done. But here you'll see a list of all your submissions your team has made, so not only you, your entire team. On that point, here's the team section. You should give it a name, and here you see all the people that's in your team. We can invite other people. Once you invite people and they accept, we can't, and just in general, can't change the team anymore. So once you're in the team, it's done. And it's a maximum of 5 people. Here you can let other people know that you're still looking for teammates if, for example, you missed the team matching events today. And here you can have your team name. So if you go back now to submissions, isn't it here? Here it's currently pending. It usually takes around roughly 20 seconds to fully grade your submission. And in this case, we get a public score of 0.39. Which is exactly the score we've gotten on our local scores, which seems to be very interesting. But again, this is only the public score. This is not the full private score yet, which will only be revealed at the end of the competition. With that being done, the final finishing touches is this discussion forum. If you have any questions about the general data, that is fine, that everyone else knows it as well. You can make a post here, or you can discuss some findings you found that you want to share with other people. You can do that there. We will make a version of this notebook we created public under the code section. And we will pin it so you guys can have access to this code as well. You can then adapt on it and improve it. Speaking of improvement, that's going to be our final section. How can we improve this score of 0.39? Well, the first and most important thing is doing more EDA, more exploratory data analysis. For example, here we've done some additional plots. Since the Rs are points in 3D, you can also just create a plot in 3D. You can do the ground track colors versus the radar cross-section. You can do some radar cross-section compared to time. And the altitude compared to the time. Additionally, we have done one fancy thing more. Why is this mouse not working properly? It's glass. So here you can see some of the things we might have shown at the beginning as well. These are 10 different tracks per radar bird, since these are real-world coordinates, all coinciding to Eemshaven. This is indeed the harbor of Eemshaven. You can plot these on Google Earth, and then see, so each color is a different type of bird. I think blue is all the seagulls, green is all the pigeons. And you can do get a real feel for how the data looks, and also find some interesting caveats. For example, if you compare it to height, you see quite consistently the yellow bird is flying the highest. I'm not sure at the top of my head which bird that actually is. For example, you can really make it important that height is an important feature. I can also look at the clutter. For example, all the white stuff is clutter, and it really looks not like anything a bird actually flies. So that's also important, that clutter seems to be very easy to identify. And what this allows us to do is generate more features in a process called feature engineering. We already engineered a feature by taking the mean of the RCS value, of the radar cross-section value. We can take a lot more features. For example, you can see how straight the bird is actually flying, and you can calculate the tortuosity of the bird. Or you can look at the thing on the bottom left, look at the climb rate, so how quickly is it ascending or is it descending. Or look at the standard deviation of the radar cross-section, because when a bird flies, it could flap its wings, and when it flaps its wings downward, it has probably a lower radar cross-section than it just has when it's completely out. And that could probably potentially also be seen here. So whenever it's open, it's has a high value, and whenever it's closed, it's a low value. And how bigger the difference is, how bigger probably the wingspan is, for example. Or how consistent, or when it's ever a bird of prey, it can just hover on for a long time, and the measurements will be quite consistent. Additionally, you can use a lot of different models. In this case, we only use the histogrammic gradient boosting classifier, but there's a lot more tabular models which you can use. Here are some examples. You can use nearest neighbors, a simple multi-layer perceptron, cat boost, TAPFN, whatever you can find, you can use. as long as it's like free to use for everyone. When you have found multiple models that are working quite well, you can build what's called an ensemble, where instead of only taking the prediction from one model, you take the predictions from all of them and average them in such a way that it actually improves the score. And this is one of the most important strategies the top people are using to win competitions. They build an ensemble which is very diverse. Ensembles work really well with models that are actually diverse, while also having a really good understanding of what each model is very good at. For example, you can have one model that's really good at classifying clutter, while others may be very good at classifying the birds of prey. On that point, you can do more research into this topic. You've already mentioned other places you can find data sets or additional input data, or you can find similar competitions that has already been existed on Kaggle or any other platform, and see what the winning solutions did there, and see if you can get any inspiration from those submissions to improve your own. Or you can also look at some white papers. In this case, you should look for time series classification. For example, here are 3 examples of time series classification, which could contain some useful information as well. And then finally, you can do hyperparameter optimization. Again, we used the histogram gradient boosting classifier, and this we just left it at the default settings. You can see there's a lot of different settings here, which you can tune and tweak, or write a script to tune and tweak it for you, which will probably improve your score dramatically. And with that, I just want to wish you the best of luck from this competition. If you have any questions, we will be sticking around here for the day. You can always email us or send us a DM on Instagram. Apart from that, happy modeling.